Have you ever wondered how the food in our body converts into energy? How medicines cure illnesses? Or how fuels help in driving vehicles? Answer to all these and similar questions is a single word: chemistry. Chemistry is the branch of science that deals with the study of the composition, structure, properties of matter, and changes that matter undergoes. What is matter? Anything that has mass and occupies space is known as matter. Before we learn more about matter, it is important that we know the importance of chemistry in our daily life. It is interlinked with other branches of science and plays an important role in our daily life. How important is it in our daily life? Let's explore. Chemistry plays a major role in identifying the weather patterns, manufacturing fertilizers, alkalis, acids, salts, dyes, polymers, drugs, soaps, detergents, metals, alloys, other inorganic and organic chemicals, and new materials that contribute in a big way to the national economy. Meeting human needs in producing food, healthcare products, and other materials aimed at improving the quality of life. Producing superconducting ceramics, conducting polymers, optical fibers, and large-scale miniature of solid-state devices. Synthesizing safer alternatives to environmentally hazardous refrigerants such as CFCs, chlorofluorocarbons, responsible for ozone depletion in the stratosphere. Understanding biochemical processes and the use of enzymes for large-scale production of chemicals, and synthesizing of new materials, which have extensive uses in various fields. In order to understand the applications of chemistry in different fields and benefit from it, it is important that we know about matter. Based on the arrangement of the constituent particles, matter can exist in three physical states: solid, liquid, and gaseous. Let's look at the description of each state along with their characteristics. In solid state, the particles are held very close to each other in an orderly fashion. Hence, there is not much freedom of movement. They have definite volume and definite shape. In liquid state, the particles are loosely held together and can therefore move around. They have definite volume but no definite shape. They take the shape of the container in which they are placed. In gaseous state, the particles are far apart as compared to those present in liquid state. Therefore, their movement is easy and fast. They have neither definitive volume nor definite shape, and they occupy the available space of the container in which they are placed. The three states of matter are interconvertible by changing the conditions of pressure or temperature. For example, on heating, a solid changes to liquid. Liquid, on further heating, changes to gaseous state at normal atmospheric pressure. Similarly, in the reverse process, gas on cooling changes to liquid, and on further cooling, liquid changes to solid. Matter can be classified as pure substances and mixtures based on the chemical composition. Substances which contain only one kind of atoms or molecules are called pure substances. And in a pure substance, the composition of a substance is fixed. For example, carbon dioxide is a pure substance which consists of only molecules of carbon dioxide, and it has carbon and oxygen in a fixed ratio. When elements or compounds are mixed together in any proportion, it results in the formation of a mixture. Thus, in a mixture, the composition varies. For example, seawater comprises of dissolved salts and water. The seawater consists of varied amounts of dissolved salts and water. Pure substances can be further classified into elements and compounds based on separation of it into its respective constituents. Substances which consist of only one kind of atoms are called elements. Examples of elements are sodium, copper, silver, hydrogen, oxygen, etc. An element cannot be further separated into its constituents by physical or chemical means. For example, oxygen consists of only oxygen atoms, and it cannot be further separated into its constituents, that is, oxygen atoms. Two or more elements combine chemically in a fixed proportion to form a compound. Examples of compounds are ammonia, water, etc. A compound cannot be further separated into its constituents by physical means, but can be separated by chemical methods. For example, oxygen and hydrogen are present in a 1:2 ratio by volume in water, and water, that is H2O, can be separated into its constituents, hydrogen and oxygen, by electrolysis, but cannot be separated into its constituents by any of the physical methods such as distillation, fractional distillation, etc. Also remember that the properties of a compound are different from those of its constituent elements. For example, the elements hydrogen and oxygen, being gaseous in nature, combine to form a compound, water, which is a liquid. Mixture can be classified further based on the uniformity of the particles present in it. If the particles are distributed uniformly throughout the solution, then it is a homogeneous mixture. For example, sugar solution is a homogeneous mixture because sugar particles get distributed uniformly throughout the solution. If the particles are not distributed uniformly throughout the solution, then it is a heterogeneous mixture. For example, sand dissolved in water is a heterogeneous mixture because sand particles are not uniformly distributed throughout the solution. A mixture can be separated into its constituents by physical methods. For example, a mixture consisting of iron filings and sulfur powder can be separated by using a magnet, that is, by magnetic separation. As we learnt, matter is anything that has mass and occupies space. Every substance is made of matter and has unique properties. We can classify properties as physical and chemical properties. Let's learn about them. We have with us a rubber ball. Let's see how we can describe it. By looking at and feeling the ball, we can see that the ball is a solid. It is round and yellow in color. It smells like rubber and it bounces. Now, let's observe this block of sulfur. We can say that sulfur is a yellow solid crystal and has a strong odor. What we saw are the physical properties of a rubber ball and sulfur. These properties can be easily seen or felt. Thus, we can say that physical properties are those properties that can be measured or observed without changing the identity or the composition of the substance. Color, length, mass, area, texture, elasticity, odor, melting point, and boiling point are examples of physical properties. Physical properties help us describe a substance. However, the description is not sufficient to identify a substance. For example, saying that sulfur is something that is yellow and solid and has a strong odor is not enough, because there can be many solids that may have the same properties, including our yellow rubber ball. Hence, it is necessary to also know the chemical properties of a substance to identify it correctly. The chemical properties of a substance can be observed when a substance undergoes a chemical change. Flammability, reactivity to an acid, and reactivity to water are examples of chemical properties. For example, if we burn sulfur, it produces a blue clear flame. Thus, the blue clear flame is a result of chemical property. When performing a chemical experiment, scientists study the properties of substances. This involves measuring the quantitative properties of a substance. A quantitative measurement comprises a numerical value and a unit. For example, this block of sulfur weighs 200 grams. Here, 200 is the number and grams is the unit. The units of measurement are derived from two systems, the English system and the metric system. The English system included units such as yard, foot, inches, miles, and gallons, to name a few. However, there was no uniformity in the conversion of one unit to another. In 1791, the French Academy of Science introduced the metric system. Under the metric system, the units of physical quantities relate to each other as multiples of power of 10. For example, 1 kilometer equals 10 to the power of 3 meters. This system was found to be convenient and hence was used worldwide. In 1960, the metric system was improved at the General Conference of Weights and Measures to create a new system called the International System of Units, or SI, which is short for System International in French. The SI unit pertains to 7 fundamental scientific quantities. They are length, measured as meter, mass measured as kilogram, time measured as second, electric current measured as ampere, thermodynamic temperature measured as Kelvin, amount of substance measured as mole, and luminous intensity measured as candela. Let's look at each quantity one by one. The SI base unit of length is meter. Meter is the length of the path travelled by light. In vacuum, during a time interval of 1/2997/92458 of a second. The SI base unit of mass is kilogram, which is equal to 2.2 pounds. As per the SI unit, kilogram is the mass of a specific cylinder of platinum-iridium alloy kept at the International Bureau of Weights and Measures in France. Thus, it can be defined as the mass of the international prototype of the kilogram. The SI base unit of time is second. It is based on the radiation from the cesium-133 atom and is defined as the duration of 9192631770 periods of the radiation, corresponding to the transition between two hyperfine levels of the ground state of the cesium-133 atom. The SI base unit of electric current is ampere. It is named after André-Marie Ampère, a physicist who discovered electromagnetism. It is defined as the constant current which will produce an attractive force of 2 × 10⁻⁻⁷ Newton per meter of length between two straight, parallel conductors of infinite length and negligible circular cross-section placed 1 meter apart in a vacuum. The SI base unit of thermodynamic temperature is Kelvin. It is the fraction of 1/273.16 of the thermodynamic temperature of triple point of water. The SI base unit to measure the amount of substance is mole. Mole is the amount of substance which contains as many elementary entities as there are in 12 grams of carbon. Elementary entities may be atoms, molecules, ions, or electrons. The seventh unit on the SI base unit is candela. Candela is the luminous intensity in a given direction of a source that emits monochromatic radiation of frequency 540 multiplied by 10⁻⁻12 Hz and has a radiant intensity in that direction of 1/683 watt per steradian. Now, let's look in detail at some common quantitative measurements that we will come across in our modules. These are mass, volume, density, and temperature. Think about it. Is mass the same as weight? Oftentimes, people consider mass and weight to be the same things. However, that is not the case. Mass is the amount of matter present in a substance, while weight is the gravitational force exerted on a substance. This implies that the mass of a substance remains constant, whereas its weight may differ from one place to another due to change in the gravitational force. For example, a person's mass is 120 kg on Earth and the calculated weight is 1,200 Newton. If you weigh the same person on the Moon, his mass would be the same, while the weight would differ. In this case, 200 Newton. This is because the gravitational force of Earth and Moon differ. Mass can be accurately measured with the help of analytical balance. Now let's look at volume. The base SI unit of volume is cubic meter. Smaller units, such as cubic centimeters, are frequently used in chemistry. Another unit of volume that is commonly used is liter. 1 liter equals 1 cubic decimeter or 1000 cubic centimeter. Some of the common devices used to measure volume of liquids are the graduated cylinder, burette and pipette. Density is the amount of mass per unit volume of the substance and can be illustrated as shown in the equation. As this unit is large, chemists often express density in grams per cubic centimeter. Finally, let's look at temperature. There are 3 scales used to measure temperature: degree Celsius, degree Fahrenheit, and Kelvin. The Celsius scale is the most common unit for temperature, and we learnt that the SI unit for temperature is Kelvin. So, let's see how the 2 scales are related. The Celsius and Kelvin scales are divided into 100 equal parts. 0 degree Celsius is equal to 273 Kelvin. Thus, we can say that the temperature in Kelvin equals temperature in Celsius plus 273. Note that, unlike Celsius and Fahrenheit, temperature in Kelvin is not referred to as a degree. Now, let's see how the Fahrenheit scale relates to the Celsius scale. The Celsius scale is divided into 100 parts, while the Fahrenheit scale is divided into 180 parts. The freezing point of water on the Celsius scale is 0 degrees, while on the Fahrenheit scale it is 32 degrees. So, 100 Celsius degree equals 180 Fahrenheit degrees, or 5 Celsius degrees equals 9 Fahrenheit degrees. We have learnt that chemistry deals with matter, and matter is made up of atoms and molecules which have extremely low masses and are present in very large numbers. Thus, chemists have to deal not only with a large number of atoms and molecules, but also with calculations containing large numbers. For example, Avogadro number is such a big number that there are 20 zeros after 6022. It is not only inconvenient to write such a large number, but also difficult to perform mathematical operations like addition, subtraction, multiplication, or division with such a number. To overcome this problem, chemists started writing large numbers using scientific notation, also known as exponential notation. In scientific notation, any number can be represented as n multiplied by 10 to the power of n, where lowercase n is an exponent having positive or negative values, and uppercase n is a coefficient that can vary between 1 and 10. Thus, we can write Avogadro number in the exponential form as 6.022 multiplied by 10 raised to the power of 23. Similarly, the number 0.04936604 is written as 4.93604 multiplied by 10 raised to the power of -2. Here, we have to move the decimal point 2 places to the right. Hence, we can say that the exponent is -2 and the coefficient is 4.93604. Now let's see how to perform mathematical calculations on numbers written in scientific notation. Let's start with addition and subtraction. If we have to add or subtract any number expressed in scientific notations, we must first check if the exponent of the numbers is the same. Only if they are same, we can add or subtract the coefficients. For example, in this equation, one exponent is 4 and the other is 3. Therefore, in order to add the numbers, first we have to make the exponents same. As 6.62 has the larger exponent, that is 4, we have to convert the exponent of 4.31 to match the larger exponent. So, we rewrite 4.31 multiplied by 10 raised to 3 as 0.431 multiplied by 10 raised to 4. Now, after taking the exponential factor in common, we add both the coefficients and obtain the result as 7.051 multiplied by 10 raised to the power of 4. The same rule applies to subtraction. The example shown here illustrates the steps to subtract two numbers. Now let's see how to multiply and divide numbers written in scientific notations. To multiply two numbers, first we add the exponents and then multiply the coefficients. For example, to multiply 2.4 multiplied by 10 raised to the power of 3 with 5.6 multiplied by 10 raised to 4. First, add the exponents and then multiply the coefficients as shown. To divide two numbers, first subtract the exponents and then divide the coefficients. Here's an illustration of dividing numbers written in scientific notations. When performing experiments, we often perform mathematical calculations on quantitative measurements to obtain accurate results. People often use the terms accuracy and precision interchangeably. But, are accuracy and precision the same? Let's see. If we have few grains of rice scattered in the plate, we can easily count them and say that they are 20 in number. However, what if we were asked to count the rice grains in this bowl? We would count them, but due to the large quantity, we may not be able to confirm if our count is accurate. One way of ascertaining the accuracy of measurement is to repeat it. Let's assume that we know that there are 105 grains in the bowl. Thus, the correct value of measurement is 105. Now, let's say we ask 4 people to count the grains, each 5 times. Shown here is the data of each person. We know that the correct value is 105. If the average value of one of the measurements is close to the correct value, then that measurement is said to be accurate. If the values of measurements are close to each other, and hence close to their average value, then the measurement is said to be precise. Let's look at the data to understand what it shows us. For person A, the average value matches the correct value. Also, the values of different measurements are close to each other. Hence, we can say that A's data is accurate and precise. For person B, the average value is not close to the correct value, but the values of different measurements are close to each other. Hence, B's data is not accurate, but it is precise. For person C, the average value matches the correct value, but there is a variation between the values of different measurements. So, C's data is accurate but not precise. Note that accuracy without precision could be a matter of chance. For person D, the average value does not match the correct value. Neither are the values of different measurements close to each other. So, D's data is neither accurate nor precise. The certainty and uncertainty in a measurement is indicated through the use of significant figures. Significant figure is the total number of certain digits in a number, including the last digit whose value is uncertain. The uncertainty is indicated by writing the certain digits and the last uncertain digit. For example, if a measurement is reported as 16.3 ml, we can say that the 16 is certain and 3 is uncertain, and the uncertainty would be plus or minus 1 in the last digit. Let's see the rules to determine the number of significant figures in a reported quantity. The first rule says that all non-zero digits are significant. For example, 897 has 3 significant figures. 0.23 has 2 significant figures, and 9.87 has 3 significant figures. According to the second rule, zeros preceding the first non-zero number are not significant. Such zeros indicates the position of decimal point. For example, 0.0325 contains 3 significant figures. The third rule is zeros between 2 non-zero digits are significant. For example, 5.01 contains 3 significant figures. The fourth rule is all zeros placed at the end or to the right of a number are significant, provided they are on the right side of the decimal point. Therefore, 0.400 has 3 significant figures. However, terminal zeros are not significant if there is no decimal point. For example, 100 has only 1 significant figure. The fifth rule says that the exact numbers or numbers that are obtained by counting rather than measuring are assumed to have infinite significant figures. For example, 8 apples have infinite significant figures, as 8 is an exact number and can be represented by writing infinite number of zeros after placing a decimal, that is 8.000000 infinitum. Now let's see how to determine significant figures in the results of mathematical calculations. While adding and subtracting numbers, the result should have the same number of digits to the right of the decimal places as the original numbers have. For example, if we add 16.25, 22.0 and 2.062, we get 40.312. Here, as 22.0 has only 1 digit after the decimal point, the result should be reported only up to 1 digit after the decimal point, which is 40.3. While multiplying, the result must be reported with the same number of significant figures as there are in the measurement with few significant figures. For example, if we multiply 12.984 by 2.5, the result is 32.46, which should be rounded off to 32, as the number 2.5 has only 2 significant figures. Similarly, if we divide 5.7634 by 1.28, the result is 4.5027. According to the rule, the result must be reported with 3 significant figures. Thus, the correct answer is 4.50. Now let's look at the rules for rounding off significant figures. The first rule is, if the last digit is greater than 5, then the preceding number is increased by 1. For example, in 1.347, if 7 has to be dropped, then the number is rounded off to 1.35. The second rule is, if the last digit to be removed is less than 5, then the preceding is not changed. For example, in 5.332, if 2 is to be dropped, then the result is rounded off to 5.33. The third rule is, if the last digit to be removed is equal to 5, then the preceding number is left as is, if it is even, else it is increased by 1. For example, if 7.45 is to be rounded off by removing 5, then it is rounded off to 7.4. However, if 7.35 is to be rounded off, then we have to increase 3 to 4, giving 7.4 as the result. When we perform mathematical calculations, sometimes we need to convert units from one system to another. This can be achieved through a method called factor label or unit factor method or dimensional analysis. Let's understand this through an example. Assume that we have to convert the length of the object from inches to centimeter. We know that 1 inch is equal to 2.54 centimeters. We can write the equation as 1 equals 1 inch divided by 2.54 centimeters or 1 equals 2.54 centimeters divided by 1 inch. The quantities 1 inch divided by 2.54 centimeters and 2.54 centimeters divided by 1 inch are known as unit conversion factors because they convert a quantity expressed in one unit to a quantity expressed in another unit. For example, if we want to convert 5 inches to centimeters, then multiply the given quantity by suitable conversion factor, retaining the units of the physical quantity and that of the conversion factor. Cancel out all the units, leaving behind only the required units. This means that numerator should have that part which is required in the desired result. Thus, 5 inches is equal to 5 inches multiplied by 2.54 centimeters by 1 inch. Thus, 5 inches is equal to 12.70 centimeters. Also note that if the conversion involves many steps, then the conversion factors are selected in such a way that the units of the preceding factor are cancelled out. Let's see an example. Let's say that we have to find the number of seconds in 3 days. We know that 1 day is equal to 24 hours. So we write the conversion factor as shown. We also know that 1 hour is equal to 60 minutes. And 1 minute is equal to 60 seconds. In this calculation, we want the answer in seconds. Hence, we will select the conversion factors in such a way that the units of the preceding factor are cancelled out. Thus, in this equation, hours, minutes, and days are cancelled out, and we obtain the answer in seconds.
The law talks about 2 types of changes, physical and chemical. Let's look at an experiment to verify the part about the physical changes. Let's place some ice cubes in a dish and weigh it. Let's say that the weight is X. If we heat the ice, it will melt and form water. If we weigh the water, we notice that the weight is the same as the weight of ice. This proves that when matter undergoes a physical change, like in this case, the total mass of the reactants is equal to the total mass of the products. Now, let's verify the part about chemical changes.
We'll fill sodium chloride and silver nitride in the two limbs of Landau's tube.
Now, let's seal both the limbs with a rubber cork.
Let's weigh the tube and note the weight. This is the weight of reactants before taking chemical reaction. Now, tilt the tube to mix the solutions thoroughly. Reaction takes place, and we notice that a white precipitate of silver chloride is formed in the tube along with sodium nitrate solution.
Let's weight the tube after the reaction. We observe that the weight remains the same. Thus, we can conclude that when matter undergoes a chemical reaction, the total mass of the reactants is equal to the total mass of the products.
That is, during any chemical reaction, matter is neither gained nor lost.
Hence, this law is also called the law of indestructibility of matter. Now let's look at the next law. Law of definite proportions. As the name suggests, this law deals with the composition of various elements present in a compound. In 1799, Joseph Proust proposed the law of definite proportions. This law states that a pure chemical compound always contains the same elements combined together in the same fixed ratio by mass. For example, the water we get from any source such as river, well, lake, sea, or from any other place always contains hydrogen and oxygen elements in the ratio of 1:8 by mass. Thus, we can say that a given compound always contains exactly the same elements in the same fixed proportion by mass. However, this law does not apply if an element exists in different isotopes, which may form a compound.
For example, if a carbon-12 isotope combines with oxygen to form carbon dioxide, the ratio of carbon to oxygen is 3:8. But if a carbon-14 isotope combines with oxygen, then the ratio of carbon to oxygen is 7:16. Another limitation of the law is that elements may combine in the same ratio, but the compounds formed may be different. For example, the compounds ethanol and dimethyl ether have the same number of carbon, hydrogen, and oxygen atoms, but their arrangement is different. That is, the compounds are different.
In 1804, Dalton proposed the law of multiple proportions. This law states that when two elements combine to form more than one chemical compound, then the masses of one of the elements that combine with the fixed mass of the other element bears a simple ratio. For example, when the elements carbon and oxygen combine, two compounds, namely carbon dioxide and carbon monoxide, can be formed.
As seen in the equation for carbon dioxide, 24 parts by mass of carbon combine with 32 parts by mass of oxygen.
Whereas, when carbon monoxide is formed, 12 parts by mass of carbon combine with 16 parts by mass of oxygen.
These masses of oxygen bear a simple ratio of 32:16 or 2:1. In these reactions, a fixed amount of carbon is combining with multiple proportions of oxygen to form carbon dioxide and carbon monoxide.
Similarly, when sulfur dioxide and sulfur trioxide are formed, the masses of oxygen bear a simple ratio of 32:48 or 2:3. In these reactions, a fixed amount of sulfur is combining with multiple proportions of oxygen to form sulfur dioxide and sulfur trioxide. In 1808, Gay-Lussac put forward a generalization which defines the relationship between volumes of gaseous reactants and products. This generalization is known as Gay-Lussac's law of combining volumes. It states that when gases combine or are produced under similar conditions of temperature and pressure, volumes of reacting gases as well as the products bear a simple ratio to one another.
For example, when one volume of hydrogen reacts with one volume of chlorine, the result is always 2 volumes of hydrogen chloride. Thus, ratio of volumes of reactants and products of this reaction is simple.
Another example is when 1 liter of nitrogen gas reacts with 3 liters of hydrogen gas to produce 2 liters of ammonia gas. Since all the reactants and products are gases, the mole ratio of nitrogen gas to hydrogen gas to ammonia gas is same as the ratio of the volume of each gas participating in the reaction. That is, 1:3:2.
In 1811,
Avogadro suggested that matter consists of 2 kinds of particles, namely atoms and molecules. He defined an atom as the smallest particle of an element, which can take part in a chemical reaction, and may or may not be capable of independent existence. A molecule is the smallest part of an element or compound which is capable of independent existence. He concluded that since the smallest particle of a gas, which can exist independently, is a molecule and not an atom, hence, the volume of gas must be related to the number of molecules. He proposed a law known as Avogadro's law, which states that Under similar conditions of temperature and pressure, equal volume of all gases contains equal number of molecules. For example, 1 volume of hydrogen combines with 1 volume of chlorine to form 2 volumes of hydrogen chloride gas. For this to be true, it would mean that the number of molecules in 1 volume of hydrogen, N, will be equal to the number of molecules in 1 volume of chlorine, N. During the reaction, they will form 2 volumes of hydrogen chloride gas, which will contain N plus N, that is, 2N number of molecules, which means that the number of molecules in 1 volume of hydrogen chloride is equal to N. Thus, proving Avogadro's law. While scientists studied matter and formed the laws of chemical combination, they were unable to answer some questions. For example, why are 2 elements different, or why do elements combine to form compounds? Dalton studied the structure of matter, and in 1808 he proposed a theory to describe the structure of matter. This theory was named after him as Dalton's atomic theory. The theory states that matter consists of extremely small, indivisible and indestructible particles called atoms. Atoms of the same element are identical in shape, size, and mass. Atoms of different elements have different sizes, masses, and chemical properties. Atoms of 2 or more elements combine in a fixed ratio to form a compound. Atoms can neither be created nor be destroyed during a chemical reaction. Chemical reactions involve combination, separation, or rearrangement of atoms. Scientists used Dalton's atomic theory for a century. However, in the beginning of the 20th century, scientists like Sir J.J. Thomson, Lord Rutherford, and Niels Bohr came up with new findings, which revealed some drawbacks in Dalton's atomic theory. The drawbacks of Dalton's atomic theory are: it could explain the laws of chemical combination only by mass, but not by gaseous volumes. It could not explain why atoms of different elements have different masses and sizes. It could not explain how and why atoms of the different elements combine to form compounds. It failed to explain the nature of binding forces between the atoms and molecules, which accounts for the existence of the 3 states of matter: solid, liquid, and gaseous. And it makes no distinction between the ultimate particles of an element or a compound. So, they modified Dalton's atomic theory, and it is now known as the modern atomic theory. Here are the key findings of the theory. An atom is no longer considered indivisible. This means that an atom is a complex structure and is made up of electrons, protons, and neutrons. Atoms of the same element may have different atomic masses. Such atoms are known as isotopes. For example, a chlorine atom may have an atomic mass of 35, and 37. Atoms of different elements may have same atomic masses. Such atoms are known as isobars. For example, a calcium atom and an argon atom have the same atomic mass, that is, 40. From this, we can also conclude that atoms of different elements may be identical in one or more aspects. The ratio in which different atoms of different elements combine may be fixed and integral, but may not always be simple. For example, the elements C, H, and O combine to form sugarcane. The ratio of the elements 12:22:11 is fixed and integral, but it's not a simple ratio. The atom is the smallest particle that takes part in a chemical reaction. In nuclear reactions, atoms of an element can be changed into another. For example, atoms of nitrogen can be changed to oxygen through bombardment of alpha rays.
On discovering that matter is made up of atoms, scientists' attention was shifted towards identifying the mass of atoms. Since atoms were small particles and could not be separated, scientists were not able to determine the actual mass of an atom by weighing it. It was possible to calculate the mass of an atom by weighing an element and then dividing the weight by the number of atoms. However, there was no method to count the number of atoms available in an element. In an attempt to find a solution to the problem in the 19th century, Dalton made some assumptions based on Gay-Lussac's findings. Based on Gay-Lussac's findings, Dalton assigned hydrogen a weight of 1. He used hydrogen as a standard for determining the atomic masses of other elements and published the first table of atomic masses. Note that the atomic masses in the table indicate relative mass and not the actual mass of the atoms, which means that the masses of elements is relative to the mass of hydrogen. In 1961, scientists met at the International Union of Pure and Applied Chemistry and decided to use carbon as the standard base. Carbon has 3 isotopes, C12, C13, and C14. Since C12 was found to be the most abundant, it was taken as the standard scale. By that time, due to the advancement of technology, scientists started using a mass spectrometer to calculate the accurate atomic mass of elements. The atomic mass of carbon was determined using a spectrometer and was found to be 12 atomic mass unit AMU. All other atoms were assigned a mass relative to the atomic mass unit of carbon. Thus, the atomic mass of an element is the number of times an atom of that element is heavier than an atom of carbon taken as 12. As carbon-12 is an isotope of carbon, it is represented as 12C. Therefore, one atomic mass unit is defined as a mass equal to 1/12 the mass of carbon-12 isotope. And the value of one atomic mass unit was determined to be 1.66056 multiplied by 10 raised to minus 24 gram. Let's determine the atomic mass unit of hydrogen based on this formula. We know that one atomic mass unit
is equal to 1.66056 multiplied by 10 raised to minus 24 gram. The mass of a hydrogen atom was determined using a spectrometer and was found to be 1.6736 multiplied by 10 raised to minus 24 gram. Therefore, in terms of atomic mass unit, the mass of an atom of hydrogen atom is said to be 1.008 AMU. When chemists expressed atomic mass on carbon-12 scale, they named it as unified scale, and the unit was represented as U instead of AMU. Though AMU is still used in most places, chemists now use U as the unit. Hence, we can represent atomic mass of hydrogen as 1.008 or 1U, and that of oxygen as 15.9994 or 16U. We know that when atoms of the same elements possess different atomic masses, they are known as isotopes. Hence, for isotopes, the average value of the atomic masses is considered as the atomic mass unit. For example, chlorine has two isotopes with average atomic masses of 34.97 and 36.97 units respectively. The relative abundance of the isotopes is 0.755 and 0.245 respectively. Relative abundance refers to the abundance isotopes of an element, as naturally found on a planet. Average atomic mass of an isotope is the sum of abundance of each isotope multiplied by the precise atomic mass. Thus, the average atomic mass of chlorine is calculated as 35.46 U. Hence, the average atomic mass was redefined as the atomic mass of an element is the average relative mass of its atoms as compared with an atom of carbon-12 taken as 12U. We can also calculate the average atomic mass using fractional abundances of isotopes of an element. Fractional abundance of an isotope is the fraction of total number of atoms that is comprised of that particular isotope. The formula for calculating an average atomic mass from fractional abundance is fractional abundance multiplied by atomic mass of that fraction. Thus, the average atomic mass will be the sum of the products of fractional abundance of the isotopes and their corresponding mass numbers. For example, neon consists of three isotopes: neon 20, neon 21, and neon 22, which have mass numbers and fractional abundances as shown in the table. The average atomic mass of neon will be calculated 20.179 U. When the atomic mass of an element is expressed in grams, it is called gram atomic mass. Gram atomic mass is also called 1 gram atom of the element. For example, 1 gram of magnesium is equal to its atomic mass expressed in gram, which is 24 gram. Like atoms, molecules are also very small. Hence, their mass cannot be determined by weighing them. Therefore, the molecular mass is determined relative to the mass of carbon atom taken as 12U. The molecular mass of substance, element, or compound is the number of times the molecule of the substance is heavier than 1/12 the mass of an atom of carbon-12. In other words, we can say that the molecular mass of a substance is the average relative mass of its molecules as compared with the mass of an atom of carbon-12 isotope taken as 12U. The molecular mass of any element or compound can be calculated by adding the atomic mass of all the atoms present in one molecule of that element or compound. For example, the molecular mass of water will be the atomic mass of 2 atoms of hydrogen plus the atomic mass of 1 atom of oxygen, which is 18.02 U. When the molecular mass is expressed in grams, it is known as gram molecular mass. Gram molecular mass is also called 1 gram molecule of the substance. For example, 1 gram molecule of water is 18 grams. Lastly, let us look at ionic compounds. Ionic compounds such as sodium chloride or potassium nitrate do not contain discrete molecules as their constituent unit. The ions in such compounds are closely packed in a 3-dimensional structure. For example, in the sodium chloride crystal, an ionic bond is formed between a sodium ion and a chloride ion. However, in its crystalline form, each sodium ion is surrounded by 6 chloride ions. So, we have to calculate the formula mass instead of the molecular mass. Formula mass is the sum of atomic masses of atoms present in one formula unit. Thus, the formula mass of sodium chloride is the atomic mass of sodium plus the atomic mass of chlorine, which is 58.5 U. When the formula mass is expressed in grams, it is known as gram formula mass.
Before we begin, let's step into a store to buy some apples. Let's say we need 24 apples. When we collect them, we get them in 2 boxes, with 1 dozen or 12 apples in each box. Here, dozen is a unit of measurement that helps us simplify and state a large quantity, like 12. When scientists were working with elements and compounds, they felt the need to have a unit of measurement to count entities at the microscopic level. Thus, the SI base unit, mole, was introduced. Mole is the amount of substance which contains as many elementary entities as there are in 12 grams of carbon. Elementary entities may be atoms, molecules, ions, electrons, or protons. Note that 1 mole of a substance always contains the same number of entities, irrespective of the identity and kind of the substance. The term mole is used to count particles such as atoms, molecules, ions, electrons, and protons. Hence, we must indicate the nature of the particle under observation. For example, saying 1 mole of hydrogen would be incorrect. We need to specify the entity we are referring to. That is, hydrogen atoms or hydrogen molecules. Thus, the correct term would be 1 mole of hydrogen atoms or 1 mole of hydrogen molecules. But what is the value of a mole? Let's find out. We know that a carbon-12 atom is used as a base to calculate the atomic mass of elements. Hence, scientists used carbon as the base to determine the value of 1 mole. They used a mass spectrometer to determine the mass of a carbon-12 atom and found it to be 1.992648 multiplied by 10 raised to minus 23 gram. They then divided 12 gram moles of carbon-12 by the mass of carbon-12 and obtained 6.0221367 multiplied by 10 raised to 23, which is the number of atoms in 1 mole or 12 gram of carbon. This is the value of 1 mole and is known as Avogadro's number or Avogadro's constant, in the honor of Amedeo Avogadro, and is usually represented as Na. Avogadro's number or Avogadro's constant is defined as the number of elementary entities, atoms or molecules or ions in 1 mole of a substance. Thus, we can say that 1 mole of water molecules contains 6.022 multiplied by 10 raised to 23 water molecules. Having found the number of moles in a substance, we can determine the mass of a mole, also known as molar mass. Molar mass is the mass of 1 mole of substance expressed in grams. The molar mass is numerically equivalent to the atomic or molecular or formula mass in U. Let's determine the molar mass of water. We know that water comprises 2 hydrogen atoms and 1 oxygen atom. We can obtain the atomic masses of hydrogen and oxygen from the periodic table. The atomic mass of hydrogen is 1.00794 and the atomic mass of oxygen is 15.9994. If we add the atomic masses of 2 hydrogen atoms and 1 oxygen atom, we get the molar mass of water as 18.02 gram. We've learnt that molecular mass of a substance can be obtained by adding the atomic masses of all the atoms present in 1 molecule of the substance, and the molar mass is numerically equivalent to the atomic or molecular or formula mass in U. Thus, we can conclude that the mass of 1 mole of any substance is equal to its molecular mass. We have seen how to determine the number of entities present in a substance. At times, scientists also require to know the percentage of elements present in a compound. This information helps to determine the purity of the chemical compound under observation. The percentage composition of elements or constituent in a compound is the number of parts by mass of that element or constituent present in 100 parts by molar mass of the compound. Let's look at an example. We know that the molar mass of water is 18.02 grams. Based on this, we can calculate the percentage of hydrogen and oxygen as shown. Thus, the percentage of oxygen and hydrogen in water is 88.79 and 11.18 respectively. Molar mass and percentage composition helps us understand the quantitative data associated with a chemical compound. But how does one arrive at the chemical formula of a compound? In other words, how did scientists obtain the formula H2O? The chemical formula of a compound is derived from 2 parts, the empirical formula and the molecular formula. The empirical formula is defined as the formula which gives the simplest whole number ratio of the different atoms present in 1 molecule of the compound. For example, the empirical formula of water is H2O. This indicates that in water, 2 hydrogen atoms are present for each oxygen atom. Similarly, the empirical formula of glucose is CH2O. This indicates that there is 1 carbon atom for every 2 hydrogen and 1 oxygen atoms. Note that the empirical formula only indicates the atomic ratio of the elements present in one molecule of the compound. Now, let's look at molecular formula. The molecular formula is defined as the formula which gives the actual number of atoms of various elements present in one molecule of a compound. In case of water, the molecular formula is H2O, same as the empirical formula, because 1 molecule of water contains 2 atoms of hydrogen and 1 atom of oxygen. In case of glucose, the molecular formula is C6H12O6. This means that 1 molecule of glucose has 6 carbon atoms, 12 hydrogen atoms and 6 oxygen atoms. The molecular formula of a compound is an integral multiple of the empirical formula. The equation can be illustrated as shown. The value of N can be obtained by dividing the molecular mass with the empirical formula mass. The empirical formula mass is the sum of the atomic masses of the atoms present in the element. Let's say we have a compound CH2. The empirical formula of the compound will be the sum of the atomic masses of 1 carbon atom and 2 hydrogen atoms, which is 14 gram-mole. Now, let's say that we know the molecular mass of the compound is 28 gram-mole. Thus, 28 divided by 14 gives us 2. Then, we multiply 2 by the empirical formula and get C2H4. We've learnt how to calculate molar mass, percentage composition, empirical formula and molecular formula. But when do we apply these calculations in chemistry? Let's say we have conducted an experiment and obtained a compound that has 29.11% sodium, 40.51% sulfur, and 30.38% oxygen. And the molar mass of the compound is 158.1 gram. How can we determine the empirical and molecular formula of this compound? First, we have to convert the mass percent to gram. As we have the values in mass percent, we can consider the value of the sample as 100 gram and then convert the percent values to gram. Next, we have to determine the number of moles in each element. Divide the mass of element in gram with the atomic mass of the element. The atomic masses of various elements can be identified from the periodic table. Therefore, the relative atomic mass of sodium, sulfur, and oxygen are 23, 32.1, and 16 respectively. On substituting the values in the equation, we get the number of moles for each element as 1.266 and 1.897. Next, calculate the simplest molar ratio. Divide the moles of various elements present in the compound by the smallest quotient obtained as a result. This gives the simplest molar ratio as 1:1:1.5. if the ratios are not whole numbers. Then multiply the number with suitable integer to convert them into whole numbers. In this case, if we multiply all values by 2, we get all ratios as whole numbers. That is, 2:2:3. Write the empirical formula by mentioning the numbers after writing the symbols of respective elements. First, write the element symbols next to each other. Then, insert the obtained numerical value of the simplest whole number ratio at the lower right-hand corner of each symbol. This gives the empirical formula of the compound. That is, Na2S2O3. Now, let's see the steps to determine the molecular formula. First, calculate the empirical formula mass. The empirical formula mass can be obtained by adding the atomic masses of all the atoms present in the empirical formula, which is 158.1 gram. Now, divide the molar mass by the empirical formula mass to identify the value of N, which we get as 1. Then, molecular formula of a compound can be determined by multiplying empirical formula of the compound with N. In this case, the molecular formula will be the same as the empirical formula. That is, Na2S2O3.